Hello students. Today we're going to do a short review for the second exam. Obviously I'm not going to cover things in the depth that I covered in the original lectures, and all of those are posted, as well as your textbooks and the slides and all those. But let's get right to it. The format will be very similar to what you had before. So I'm going to get right into doing a review. The first thing is the first subject that we covered was metamorphic rocks. And metamorphic rocks, you know that there are uh, either igneous rocks or sedimentary rocks that have been changed through heat, pressure, chemically active fluids. And you know that they occur in these temperatures here. This is the metamorphic zone. So once you get into melting, it's no longer metamorphic, and there's some low temperature, low pressure changes that turn sediments into rocks. The metamorphic is somewhere in between, does not involve melting. And so, as I said, heat, pressure, chemically active fluids, and the heat can cause crystals to reform, cause fine crystals to grow into larger ones, and it can make it easier for the rock to be bent or deformed as well. So where does heat come from? The heat comes from usually magma. Either you're getting close to the mantle of the earth, or in some cases your magma is coming up, whether it's a hot spot, convergent plate boundary, or divergent plate boundary. You've got magma coming up, and that can create metamorphism as well. And the chemically active fluids, usually this is water with a lot of ions present. So the hot water bubbling through the rock can change its composition. I want you to know the difference between what foliation means. So foliation is when those minerals line up together. They start out being relatively random, and the more heat, the more pressure, the more lined up they get, and the rocks can look different. And this is particularly the case with shale. The shale, the more you press it, it will go through different stages of metamorphism. It'll go from being shale to being slate to being schist to being gneiss. So this is your highest grade of metamorphism, and slate is your lowest grade. And there's a few steps in between there too, with phyllite and all. But few new shale, slate, schist, gneiss, that sequence. And if you could identify them, I may give you this chart as part of the test, so you don't feel like you have to write down everything in it. But you should understand the material in that chart. So certain things like shales, they go through a whole series from fine to medium. They go through low grade to high grade metamorphism. It's very easy to tell with shales. Many other things like sandstones and limestones, they're not foliated, so it's harder to tell uh, the exact degree of metamorphism those rocks have gone through. So shale is a good indicator. So you go from mud to shale to slate to schist, phyllite, schist, gneiss, and magma. Phyllite should be, schist should be in here. It should be schist right here. But and then once you get into this stage, you're no longer in metamorphic rocks. So the gneiss is the highest grade of metamorphism. So there are different metamorphic environments. The important ones that I want you to remember: contact, hydrothermal, and regional metamorphism. Subduction metamorphism, regional metamorphism are relatively similar. So contact metamorphism is right on the edge of that plume. You get this deformation right here. I should choose a different color than that. You get deformation right along this boundary, and that's the contact metamorphic rocks. It's only 10 or 20 feet, so it's like a burn mark. And so depending on what the original mineral is, and original rock is, and I would expect you to be able to know that sand will turn to quartzite, limestone will turn to marble, shale will turn to, in this case, hornfels, but shale can also turn into slate and schist and gneiss and those things. And but so different rocks will turn into different things when exposed to contact metamorphism. So hydrothermal metamorphism is when you have basically hot water and it boils through, it gets near the magma, the water boils through all these rocks and it can change the rock and it turns basalt into serpentinite. So where all the water's bubbled through it, it makes those green veins. The most significant, the most important is burial or subduction zone metamorphism. And this is very similar to regional metamorphism. In both cases, uh, you put them down deep in the earth under a lot of heat and a lot of pressure, and it can make metamorphism for a very wide area. And regional metamorphism is a very similar thing that happens when two continents collide, as opposed to subduction metamorphism is when an ocean plate and a continent collide, or two ocean plates collide. But this regional metamorphism, it can make metamorphic rocks for hundreds of miles and different degrees of metamorphic rock. So over here you have shale, and as you get closer to where the intense pressures are, this is where the gneiss is formed. And over here is where the schist is formed. So you're getting closer to that source of incredible heat and pressure, which is all these mountains that are pressing down, and the pressure from this horizontal pressure too, that makes all these minerals become more and more lined up in certain kinds of rocks. Sandstone, limestone are never going to show foliation, but the ones that do show foliation will show it more and more as you get higher and higher pressure, so they're good indicators. So your hydrothermal morphism happens where you've got relatively low pressure but fairly high temperature, or somewhat moderate temperature. High temperature is contact metamorphism with no pressure, and then the regional and subduction zone are very high pressure, high temperature. Impact metamorphism, we had a question about nuclear bombs on the test. So a nuclear explosion, something like that, will create shock metamorphism. And a meteor hitting the earth would also create shock metamorphism. And that's when you have incredible pressure for a fraction of a second that causes these unique features, um, cracked quartz, that sort of thing. When we talk about degrees of metamorphism, as I was talking before about slate versus phyllite, schist, gneiss, um, certain minerals can be indicative of how much metamorphism you have. So if you take the mineral chlorite, that's a fairly low grade mineral. So after you get to a certain degree of pressure, the chlorite will reform into other kinds of minerals. On the other end of the spectrum, something like sillimanite, staurolite, garnet, these are indicative of very high levels of metamorphism, high grades, so more like the gneisses. So I don't expect you to memorize the things in this chart, but to recognize the principles in that chart. You could tell from a certain, if I told you it was gneiss, you'd know what kind of minerals to expect. And if I told you it was there was chlorite in it, you'd know we were talking about a fairly low grade of metamorphism, and everything in between, garnet and muscovite, are that intermediate level. And that makes sense, right? Because schists have so much mica in them, it makes sense that schist is lined up underneath where there are so many micas. Talked about earthquakes, natural phenomenon, violent shaking caused by the slippage along a fault. And we had that right here a few days ago. Actually, it was today. Today's Friday. It was an earthquake this morning that was felt in Rhode Island. So you build up strain when you have pressure along the fault. And that buildup of strain, when it's released, you have it sort of snaps, like an elastic, and the fault moves. And we talked about the strike and dip of a fault is the dip is the angle at which it dips into the earth, and you can have movement along the dip or along the strike. The strike is the line where the fault intersects the surface of the earth. So a strike slip fault, well, dip slip fault, you have hanging faults or normal faults, and it depends on which way this wall is moving. In this example, it's moving this way, so it's normal fault. If it moved this way, it would be reverse fault. And how do you tell the difference? Because it makes this hanging wall a wall. We talked about this, that you could hang on that wall. That's how it's a reverse fault. A normal fault, you just walk on it normally, right? There's the surface. You can't hang on it. Strike slip faults move along the strike, so they don't move so much at an angle. It tends to be a 90-degree fault and two blocks kind of moving next to each other, or scraping by each other, and something like the San Andreas fault. Talked about seismic waves, how P waves go through liquid and S waves don't, and this allows us, and S waves are also slower than P waves, and the two combinations, the fact that S waves won't go through a liquid and P waves will, but P waves will be bent, allows us to see that this liquid core of the earth is a liquid because the S waves won't go through it. So there's a shadow zone where you won't see any S waves because they can't go through it at all. So you won't see them on the other side of the earth. And there's also these P waves go through it, but they get bent. And the angle at which they're bent, when we see the wave on the other side of the earth, we can tell that there's a liquid inner core, outer core, and a solid inner core. And that's called refraction. So, and I mentioned P waves are faster than S waves. So we know how much faster, so we can measure how far the earthquake is away. And if we have 3 locations, we can draw a circle of how far it is away. And there's only one location on Earth where that could be, and that's the epicenter. The epicenter is that point on the Earth that's directly above the earthquake. The earthquake happened deep within the Earth, and that's the point directly above. The fault that it moved on is actually here. So the epicenter does not have to be on the fault. In fact, it won't be on the fault unless the fault is vertical. And we talked about the Richter scale. So a magnitude 4 is not twice as strong as a magnitude 2. It's thousands of times stronger, right? Because every increase in magnitude is 32 times more energy. It's a logarithmic scale. And the depth that earthquakes occur. So you know that at subduction zones, you can have deep, intermediate, and shallow earthquakes that are all very severe, or that can all be very severe. And the deep earthquakes will occur on the part of the side of the plate that is riding on top. So if a land plate collides with an ocean plate, like here in South America, that's the plate boundary, and the deep earthquakes are on the landward side of that plate boundary. Okay, and this is just a graphic explanation of why that is. We talked about different things, tsunamis, and with a tsunami, it's a wave. It's not really moving water; it's moving energy. So before a tsunami hits, they'll the water will get very, very shallow because all that water is building up for the huge wave. And the seismic gap method is a way of predicting earthquakes by that we know earthquakes are more likely to occur where there hasn't been recent movement on a fault, because that's a place where the fault is locked. And it's very approximate. You remember that earthquake in Beichuan and what caused that. The landslide dammed the river, and it was a terribly devastating thing. Okay, and all right, I have one more slideshow to show you, and that is going to be the lab show to show you, and that is going to be the lab on dating. So we will, I'll go ahead and load that. I thought I already had, but I was mistaken. Okay. So when we talked about dating rocks, we talked about the difference between relative and absolute dating, and relative dating, all those rules that we followed, and hopefully you're doing the lab and following those rules. And for a long time, all we had was relative dating. And the opposite of that is absolute dating based on radioactive decay, and that the secret there is that rocks decay at a known rate. So just while this loads, I will just talk to you about it. You know about folding of rocks, and you know how rocks, when there's heat, it's easier to bend the rock, so you can have mountain building where there's folding down below and there's faults up above, because near the surface of the earth rocks are more brittle, down below they're more ductile. So in terms of dating the rock record, we followed certain principles, and the most basic is the rocks on top are almost always going to be younger than the rocks on the bottom, because there's no way to drop a layer below in empty space below the rocks, right? That's not how rocks form. So we call that the law of superposition. There is also that sedimentary rocks are laid down horizontally. So when you find them bent, you know that they were laid down first and then bent. And when you see, say, igneous features like a dike or a sill, the one that crosses over is the younger one. The one that is bisected is the older one. And if similarly, if an intrusion goes through a sandstone, then you know the sandstone came first and then the intrusion went through it later. You can also sometimes see evidence of contact metamorphism to tell you whether or not the rock was there when the magma went through. Similarly, when you see a canyon cut through sedimentary rocks, often it's a continuous layer and the erosion happened later. Still waiting for my my slideshow to load. Maybe I can share my screen with you. Let me see if that's possible. Share. Share. Oh yeah, I can share my screen. Okay. I will share this with you now, so we can start, so we can go through. Okay. All right, so hopefully you can see my screen now. Okay, so as I mentioned, sedimentary layers are often contiguous for a large Didn't mean to do that. They're often contiguous for a fairly over a long distance. And when you see canyons and things cut through them, you know that it was probably a continuous layer of sandstone that later got eroded. All right. So cross-cutting relationships, again, a fault goes through separates out the rocks. You know that the rocks came first and then the fault came later. When dikes go through rocks, if dikes cut through each other, the one that cuts through is newer. If there's signs of contact metamorphism, that can help you. And there's going to be inclusions of rock. An inclusion is a piece of one rock that goes in another kind of rock. If there's, say, sedimentary rock in the igneous rock, then the sedimentary was there first and it got melted into, included into the magma. If, on the other hand, there is part of the igneous rock in the sedimentary rock, then that means that the igneous rock was there first, it eroded, and pieces of it wound up in the sedimentary rock. So when you see a lava flow like this, you can tell based on inclusions as well as contact metamorphism which one came first. Okay. And this is just a further explanation of inclusion. I won't go into. It's rare. Well, sedimentary rocks can be continuous for a long period of time, but it's rare to find a column at some point that doesn't have some kind of unconformity in it, or a period where there was no erosion, or a period where rocks were laid down and later they were eroded. No, I said no erosion, no deposition. Either no rocks were deposited in that time or they were deposited and then taken away by erosion. So we call that hiatus an unconformity. Okay, so I'm going to stop sharing my screen and start sharing my my slides because it's finally loaded and it's easier to do that. So here is the unconformities again. So you can see that refers to the hiatus where you didn't have any deposition or you had erosion. So you can have a disconformity, angular unconformity, or nonconformity. Disconformity, it's not really obvious, but you have this period where sedimentary rocks were laid down, then you had erosion, non-deposition, and then you had more sedimentary rocks laid down. There's no folding, there's no faulting, there's really no anything to make a stark contrast. And that's going to be very different from an angular unconformity where you had these rocks being laid down horizontally and then you had folding. So this fold probably goes something like this for this layer of rock. It folds and then it gets eroded away. And when it gets eroded away, you are left with as you erode all these parts of the rock away, you're left with an angular surface where that rock meets the ground, and then later on it gets submerged and you have more deposition on that angular surface and you have continuous deposition, so you have an angular unconformity. It's very obvious to see. You can see it in this picture. I showed you a few pictures of angular unconformities. It's another one. A nonconformity is where the one below it is not a sedimentary rock. So it doesn't have any layers. And the Grand Canyon, the Great Unconformity, which is like a billion-year gap, is an example of that, where you have an igneous rock down below and you have sedimentary rocks up above, and the sedimentary rocks have layers, the igneous rocks don't. Or metamorphic rocks often don't have layers too. Okay, so that is an example of angular unconformities. And you can look at the Grand Canyon, you can see all of those things. And so I'd expect you to be able to look at, if I gave you any kind of diagram like this, you'd be able to say, well, which one came, what came first, you know? Deposition came first, and then you had tilting, and then you had an unconformity form. I guess, well, deposition came first in this case. Deposition came first, um, and it got buried, turned into rock. Then you had an igneous intrusion come up here, and then you had folding, and so it all got tilted at an angle, and folding and uplift and erosion. And then after that, it got buried again underwater, and you had another layer of sedimentary rocks. And you can tell all that. You can tell that whole sequence of events. And then it got uplifted again. Why? Because the sedimentary rocks were formed in the ocean, and it's not in the ocean now. Okay, so, and there are a few examples here. And again, you should be able to work those out if I gave you diagrams where you can figure out the sequence of events. And I won't go through them all here. A lot of them are part of your lab exercise. Then we talked about absolute dating. Absolute dating, when you say exactly how old or approximately how old in years, everything else is relative. These are in years, and that's because the reason this works is because radioactive elements decay at very consistent known rates, and nothing you can do to them, heating them or making them wet, or it doesn't seem to affect it at all. It's very constant. But we can only do absolute dating on certain kinds of rocks. We can only do them on igneous rocks, and we can also do them carbon dating on certain living tissues, but that only goes back 50,000 years. So geologically, that's not very old. So the stuff that's geologically even a little bit, stuff that's even a little bit old is radioactive dating is only going to be possible with igneous rocks. Metamorphic sedimentary rocks basically do not subject themselves to radioactive dating. And the principle of how the parent decays into the daughters, and in a half-life, and that half-life is the time it takes half of the parent to turn into the daughter. And each subsequent cycle, it doesn't change. So in the first half-life, half of them will turn into the daughter products. In the next half-life, same period of time, if it's a billion years, after a billion years, half of them, after 2 billion, it'll be a quarter of them are still the parent, and after 3 half-lives, it'll be 13%. And it'll keep going down and down like that, cutting in half every half-life. Did an exercise flipping the coin where we understood that. And knowing those absolute dates of igneous rocks may help you pin down an approximate date for all the sedimentary rocks that are in between those dates. You can also correlate with fossils, and fossils evolve over time, so that can give you some idea with sedimentary rocks. Now that we have had enough data from around the world to know when different species evolve, we can get a pretty good guess on the time, but it's not as precise as radiocarbon dating, radioactive dating. Ash layers are awesome because they coincide with the sedimentary rocks, and they can tell us, give us a good time for when those rocks were deposited. And we talked about correlating rock units from widely varying locations based on some of that dating. All right, well, that is my review. So I know that was fast, but it goes a lot slower in the lectures that I published, and make sure study the appropriate chapters in your book and look at the slideshows from the other lectures and do the best you can. You know, the essays, try to be as complete as possible in answering those essays. And good luck. I will see you all on Monday.